This is Dr. Holt. I want to go over this UT problem. Here you have a window. It's 4.3 meters tall. You have a ball that has been dropped from a certain height. It comes down here to the top of the window, and then it proceeds. And during the time it goes from here to here, it takes 0.161 seconds. What we're looking to find on this problem here is we want to find out what is this distance here from the top of the building to the top of the window. Alright, to set up a problem right here, let's let time equal to 0 be right here. Let this be your VI, and we'll let time here equal to 0.161 seconds, and we'll let this be our VF. Alright, so now let's go back to our kinematic equations and see if we can solve this. So we know that final velocity is equal to initial velocity minus 9.8 times t. And we do know that, so we'll use that equation. So we say VF is equal to VI minus 9.8 times our 0.161 seconds. All right, run that number real quick. Grab my calculator. All right, we got 9.8 times times 0.161. That's going to give us 1.5778. Okay, so our equation is going to give us this. And I'm going to drop the vector hat. So VF is equal to VI minus 1.5778. Alright, so that's our first equation we were able to generate. Alright, now we think about what do we know? We know distance traveled during here. So we can go back to our equation that says that VF squared is equal to VI squared minus 2 times 9.8 times delta y. Alright, what we're going to do here is, since we can substitute back in, hopefully we'll have one unknown. Now we know our delta y in this, we can take this out and put in negative 4.3. Alright, well, while we're here, I'll just rewrite the equation. VF squared is equal to VI squared. And then that value there is going to give me 84.28. And again, that's positive. Okay, substitute this back into here. That becomes VI minus 1.5778 squared is equal to VI squared plus 84.28. Okay, what you're going to have to do here is you're going to have to FOIL that. When you do, you'll get VI squared minus 3.1556 VI plus 2.489 is equal to VI squared plus 84.28. Alright. At this point in time, just subtract VI squared from both sides, and you're going to lose it here and here. So that's gone. So now you have a simple equation. You only have one unknown. So now we can solve this problem. Move this to the other side. That gives me negative 3.1556 VI is equal to 84.28 minus the 2.489. When we solve for that, we will find that VI is going to give me a value of negative 25.919 meters per second. Alright, so that's velocity at the top of the window. That's the top. Now, we look at the problem a little bit differently, and I'll just kind of draw like a line being representing the top. I'll just come down here. Oops. Okay, the ball was dropped. We're letting this right here be the top of the window. So the window is sitting in here just like this. Okay, we're going to drop the object from the top of the window, clone that, bring this down here, and we know at the top of the window we're traveling this velocity. Make do that the vector. And that value there would be 25.919 meters per second. Alright, we do know our velocity here initially in the y direction would be 0 because it's dropped. So we can go back to the equation Vf squared is equal to Vi squared plus 2 times our acceleration times delta y. Now we know here this will be our final velocity at this time, whatever time it takes to go from here to here. So we put in 25.919 squared is equal to, this value is going to be 0 plus 2 times negative 9.8 times delta y. Solve for delta y and you will get delta y is going to equal to, now this value will give you, it's going to give you a displacement, so it's going to give you negative 34.276 meters. So our answer from here, the window above, would be 34.276 meters. And that would be your correct answer. Alright, so those are the steps you're going to need to do the window problem on UT. Again, follow my approach, and basically you end up getting two equations, two unknowns, and you just substitute back in because you're able to write this one equation. Alright, best of luck.